Okay, so in lecture two, we talked about particle kinetics. In particular, we focused on the force and acceleration method. In today's lecture, what we'll do is we'll elaborate and expand the methodologies that we discussed last time. This time, we will talk about planar kinetics when it comes to force and acceleration methods. And so, of course, if you're concerned with planar beings, you are looking at the two-dimensional aspects of them. So you could have translations, you could have these translations in the x and y directions, you can also have rotations. So the first thing we want to do is we want to set up some mathematical preliminaries. One of them is the mass moment of inertia. We want to talk about that a little bit. And then we want to also talk about parallel axis theorem, which applies in theory of structures and structural analysis type classes as well. So let's do that. Mass moment of inertia is really the mathematical equivalent of mass for rotation. So whatever mass was to a translational being, mass moment of inertia is the same thing, but for rotational behaviors. And the way we want to formulate it is we set up an axis, kind of like this. And then we have our two-dimensional body. In this case, we have this potato. And then, for every increment of this potato, we could have a delta m, which is the incremental mass. And this incremental mass is our distance away from the axis. And so this distance is at a perpendicular angle to the axis. And so with this schematic in mind, we could set the definition of mass moment of inertia as I is equal to r squared dm, and typically this ends up having units of kilogram meter squared. And of course, if we want to be even more mathematical, we could say we're integrating over the entire volume. So this is the entire volume that we're considering. There is another definition that sort of normalizes your mass moment of inertia, and this is the radius of gyration. Radius of gyration is basically has units of distance. It's either feet, meters, inches, and it's basically given the abbreviation k, or the variable k divided by, it's I divided by m, square root. And of course, it ends up having units of feet or meters or as such. So this is another useful mathematical describer for mass moment of inertia. So if you have k, if you have the mass, then you can guess what I value is. So here is one important concept. Another important concept to discuss is the parallel axis theorem. Parallel axis theorem comes in handy whenever the center of rotation becomes off center relative to the axis that we're considering, or whenever we have bodies that are composites, so we have multiple shapes that are attached to each other, and we want to see what the totality of the moment of inertia is. So that's where we're going to set up now. So again, imagine we have this reference axis. Imagine we have this potato, and then the potato has its own centroid, and we call this G. And if G in this case is off by a distance of d from the axis of interest, then what we could say is that, and of course, maybe let's call this axis A, and let's call this axis B, around which G is rotating. Then what we could say is mass moment of inertia about axis A is equal to IB plus MD squared, where M is the mass of the potato here, and D is the distance from the centroid of the potato to the new axis G. So we call this the parallel axis theorem relationship, or PAT. So now we can talk about the planar kinetics, and we can talk about the fundamental equations of motion that need to be considered when it comes to planar bodies. Again, remember, this is a two-dimensional body that we're considering. There are translations, there are rotations, and these all need to be incorporated into your equations of motion. So generally speaking, if we have the following schematic, if we have a following body and, there are some alphas and some omegas, these are the angular velocities and accelerations. And then, if we have, let's say, some forces that are being applied, maybe an F1, F2, ... F of n. Maybe we even have some moments. M1, M2, Mn. And of course, we have a centroid whenever we have a mass. So whenever we have a scenario like this, we can relate all these different forces and moments to the accelerations that exist, because really the basis of today's lecture is the force and acceleration method. So let's say we have the centroid O, around which the potato here is rotating. What I can do is I can draw the approximate trajectory of point G, kind of like this. And so you can imagine point G is rotating around this point O. And when it's rotating, we expect an inertial acceleration heading outwards. It's always away from the centroid. And if we are maybe going in the counterclockwise direction, if the potato is rotating in the counterclockwise direction, the tangential force at G will be in the opposite direction, sort of like this. So we could term these as AGT and AGN, right? So these are the accelerations that exist. And really, the goal here now is to connect these forces, these moments, these rotations to these accelerations that we have. These are the descriptions that we want to do. So right off the bat, we know that AGN is equal to omega squared R of G. R of G being this distance here, right? We also know that AGT is equal to alpha R of G, right? So the centripetal acceleration we have is dependent on the angular velocity. So omega squared times R of G gives us centripetal acceleration, AG of n. And then our tangential acceleration is really dependent on the rotational acceleration alpha. So we have alpha, R of G, and that's really what we get. So with this in mind, we could say sum of forces in the normal direction. And of course, here I'm using the term normal tangential. You could also refer to this as X and Y, depending on the type of coordinate system you have. So, let's say if you have such a system, X and Y, you could easily rephrase the formulation we have here. So sigma F of n is equal to M A G of n. That is the fundamental relationship for the force and acceleration method. A G of n can be plugged in as, so that's the plug-in. Then we could say, what are the sum of forces in the tangential direction? These are mass AG of t. And of course, AG of t could be plugged in as well. So we've got this. And lastly, we could say, what are the sum of moments, right? So we've talked about translations about the two different axes that we have. We also want to look at rotation. So sum of moments about point G are equal to IG alpha, and that's it. So IG here is the mass moment of inertia about point G. So this is really where IG is relative to. We could also rephrase this third relationship. We could say we have sigma MO, so sum of moments around point O, equals to IO alpha. So the same rotation, acceleration, but different mass moments of inertia. If you're doing sum of moments about a different point, your mass moment of inertia will change. You will have to recenter the centroid axis using parallel axis theorem. So for the second relationship, this is the axis that we're talking about, and it's an axis that's coming out of the page. So if you're looking at your computer screen, the axis is coming right at you. So that's what that is. All right, good. So now we are in a good spot to look at an example, and really this methodology is not complex. It builds on everything we've done so far from lecture 2, from some of the kinematics that we discussed. All we have to do is, this time, we have to utilize more than one equation of motion. So we've got this example with this body that is clearly a composite. There are two shapes that we're looking at. And the way I want to describe this is via segments 1 and segment 2. Segment 1 here is a slender rod, and segment 2 is a sphere. And these are carefully selected terms because they imply very specific mathematical mass moments of inertia. So the way we can calculate the mass moments of inertia really have to do with these definitions. Now, what the question is asking us to do is to determine the angular acceleration alpha for this problem and the magnitude of the reaction at point O at the exact moment that is shown. So there is a 30-degree angle, right? This shape is at a 30-degree angle from the horizontal axis. And our goal is to compute the following behaviors. The first thing we want to do is to compute the mass moments of inertia. And doing this requires us to use two mathematical formulations. And by the way, before I completely forget, the length of this slender rod is L is equal to 800 millimeters, right? So for the first shape, the slender rod, I1 is equal to, and this is I about the centroid of this mass, so it's around this point. I1 here is equal to 1 over 12 m1 L squared. And this is a very standard mass moment of inertia equation for a slender rod. It's looking at the rotation about the centroid of this body, and you could look this up in any sort of textbook or any sort of online source. We already have L, we already have M1. We plug these in and we get 1.6 kilogram meter squared. So that's I1. Next up, we want to look at I2. So this is for the second shape. The second shape is a sphere, and when we're looking at its centroid being down its center, the middle, I2 ends up looking like this: 2 over 5 m2 r squared. We already have r, we already have m2. Plugging these in gives us 1.28 kilogram meter squared. So that's very good. We have two mass moments of inertia. This is the very beginning of the problem. We've set up some of the geometric preliminaries that are important. Something else I want to add is maybe it's important to look at how far the centroid of these shapes are from point O. So if I'm looking at R1 here, or if I'm looking at R2 here, what are these distances? That might also come into play. So let's just try to figure this out too. R1 here is equal to 0.4 meters. So it's the 800 millimeters divided by 2. R2 is, it's basically the 800 millimeters plus the radius of the sphere. So that gives us to, that gets us to 1 meter. So that's 1.0 meter. So that's all the mathematical preliminaries. The next important step when we're setting up is free body diagram. So we're looking at the free body diagram. For the free body diagram, we have several things to consider, right? We want to draw the shape, first of all, exactly in accordance to the angle that's given to us, because that's important. Oops, that's a really big sphere. This is the shape that we end up getting. And then I maybe want to select a couple of arbitrary directions for the reactions. So maybe I have O normal, O tangential, right? I already know this angle here is the 30 degrees that's given to me. This is prescribed by the problem. In addition, I know that there are several centroids that need to be looked at here. This is distance to centroid 1. This here is distance to centroid 2. We have point G1 and we have point G2, which R1 and R2 are measuring from point O. Now, think about the problem this way. The way the problem is prescribed, omega is given to us as a clockwise rotation, right? So you're rotating this, this composite body in a clockwise direction. How do you expect the forces to be reacting? And, by the end of this lecture, this is the kind of intuition I want you to have. Wherever the body is rotating, the inertial accelerations will be in the opposite direction. So if I'm looking at point G1, if I'm rotating clockwise, G1 is going to act in the counterclockwise direction. So it will go in this direction. And perhaps I can use a different color. It will go in this direction. Same thing is true for G2. If I'm going in the clockwise direction, I expect G2 to be reacting in the counterclockwise direction, right? So that's one part of it. We've looked at the tangential components. We also want to look at the centripetal components, or the normal component. If I am rotating around point O, right? Point O is the centroid of my rotation, then the centripetal accelerations will be heading outwards and away from the centroid of acceleration. So this here will be my the direction of my normal acceleration for G1, and this will be for G2. In addition to all of this, I know that the entire body is rotating clockwise, so I expect a general rotational inertia as well. So what you're seeing here is there are three components that we're dealing with. We have tangential components, we have a normal component, and we have a rotational component. These are all elements of the three equations of motion that we need to address right now. So what I want to do now is I want to take these 2 points, G1 and G2, and I want to zoom in on them a little bit more. So for mass 1, we get the following. We have the tangential component, so we get M1, R1 alpha, where R1 alpha is a tangential at this point. We have some of the values given to us, so when we plug this in, we get 12 alpha. We already know M1, we already know R1. So we plug that in, and that's what we have. For the normal components, we have m1, r1, omega squared. This time we know m1, we know r1, and we know omega. So plugging all of this in, we get 17.28 newtons, because the whole thing is given to us. And then for the rotational components, we have I1 alpha. And I1 is already computed. We plug it right in. It's 1.6 alpha. Okay, so now zooming in on mass 2, we are looking at the tangential components. Again, it's M2, R2, alpha. The alpha is the same between G1 and G2 because the mass is rigid. It's a rigid body that's rotating, so you're expecting similar angular accelerations. So M2, R2, alpha gives us the tangential acceleration times the mass. So we have 80 alpha if we plug in all the correct parameters. And then for the normal components, we have M2, that's the mass, times the centripetal acceleration, which is R2 omega squared. And again, because it's a rigid body, the omegas that we're expecting are also the same. So here we get 115.2 newtons. And lastly, the rotational component is basically I2 alpha, and we already know I2. So we have 1.28 alpha. Okay, so let's set up the equations of motion. So here we have, let's say, a sum of the moments around point O equal to 0. Now, once you get to know this methodology, you don't really have to do sum of moments around the centroid of rotation. You could do this around really any point, whichever is convenient for the problem you were given. For this problem, I selected point O, and I selected the following sign notation, meaning clockwise is positive, because there are certain conveniences that I'm going for. So here we have, let's see, we have 0 is equal to, obviously in the rigid body that we have the two weights. So we have these, so I want to incorporate those. So we have W1, weight 1, 0.4 cosine 30. That gives us the horizontal shadow of the rigid body, of the first component of it. And then we have W2. So we have this. And then we want to incorporate the inertial components. We have 1.6 alpha, that's a minus because it's going in the opposite direction. We have minus 12 alpha 0.4. So that's looking at the tangential force times the moment arm, minus 1.28 alpha. This here is the rotational inertia for point 2, minus 80 alpha times 1.0. So all of this is equal to 0 as we have set up. And when we compute this, alpha ends up equaling to 8.905 radian per second squared. So that really addresses the first part of the problem, which was given the circumstances, what is the acceleration for the angular direction? And then we could do a number of other things if we're interested in the reactions at point O. We could say sum of forces along the sigma ft direction. This must equal to 0. So we have minus the reaction force in the tangential direction plus 12 alpha plus 80 alpha minus W1 cosine 30 minus W2 cosine 30 equals to 0. And these W's and the cosines are basically looking at the contribution of gravity to the tangential force direction. And this is one equation, one unknown. We already know alpha, and OT is basically equal to 114.3 newtons. Okay, good. That's one component. We need to find out what the other component is, for which we could do this diagonal direction, positive sigma F normal is equal to 0. So that's the third and final equation of motion. Setting it up, we have the following. These are the forces we had. Minus W sine 30 minus W2 sine 30 is equal to 0. And ON is equal to 671.5 newtons. So that's what we have. And of course, because we're looking at forces in two different directions, in the tangential and normal directions, we could always sum them together using the square root law. So this is generally how we go about doing so. And this gives us a sum of reaction forces as 681.2 newtons. So that's about it. That is the kinetics of planar bodies using the force and acceleration method. See you next time.